Welcome back to Speller Tutorial Services. In today's video we're going to prove this expression for this series is true by using induction. And basically we want to prove that that expression is true for all the positive values of n. Alright, we begin this proof by first saying that we're going to look at s sub 1. With s sub 1 we're saying that if we take the n value and take the variable n and give it a value of 1, that the first term is going to come out to be a 4. So we need to go ahead and prove that. Let's take this expression, 2 times the quantity 3 raised to the n. Well, n is going to be 1 minus 1. Well, 3 to the first power is 3, and then 3 minus 1 is 2. So we end up with 2 times 2, which does come out to be 4. Our second step is to make sure, or is to assume that if s sub k is true, then s sub k plus 1 is also true. So basically what we're going to say is if we restate this series and this expression in terms of k, and then we restate it again in terms of k plus 1, meaning the very next term in the series, then we'll be able to use a proof by induction to prove that that expression is true. And so the first thing we do, we take this s sub k, and we're actually going to rewrite our series here. So 4 plus 12 plus 36 ellipse plus 4 times 3. Instead of n, I'm going to write k minus 1 is equal to 2 times 3. Again, the n becomes a k minus 1. And now I'm going to rewrite this using the k plus 1 term, meaning finding the term that comes after this last term. So let's begin by restating. So 4 plus 12 plus 36 plus ellipse. And now I'm going to rewrite this. This here was previously the last term, but now I want to write the next term that comes after it. In writing the next term, that just means I'm going to add 1 to my k value. So I rewrite this last term, 3 raised to the k minus 1, but I need to add 1 to that because I'm going to the next term. And I also need to do that to the expression here at the end. 3 raised to the k plus 1 minus 1. Now I need to begin some simplification. Let's look at this last term here. With this last term I have a negative 1 and a positive 1, which I know resolves down to 0. So I can rewrite this last term as 4 times 3 raised to the k. And let me go ahead and rewrite everything here to the right hand side. 3 to the k plus 1 minus 1. And now I want you to notice that if I'm just talking about this portion here of the series, notice that what's in the box matches the s sub k that I have here above it. And the shorthand notation for this series is this expression here. So that means that I can swap out what's in the box region with this expression. So I'm going to do that down here. So I'm rewriting all these terms as this one simpler expression. And that expression we see as 2 times the quantity 3 raised to the k minus 1 plus that last term. Now what I need to do is to use algebra to make this left hand side look like the right hand side. And if I can do that, that's going to prove this series is true for all positive values of n by using induction. First thing I notice is that I have a GCF of 2. So I can factor out a 2 from this term and a factor out a 2 from this term here. Or these are factors, but this entire thing is one term. This entire thing is the second term. They have a factor of 2 that's shared. So let's factor out a 2. So this leaves me with the 3 raised to the k minus 1 plus 2 times 3 raised to the k, because I factored out a 2 from that 4. Square bracket to close that off. And I'm not going to rewrite, just use this caret marks to show that this expression is now here, is now down here. Next thing I notice is that I can rewrite everything inside the, or not rewrite, but reorder the terms inside of my square brackets to make it easier to factor inside there. So let's group these. Let's the 3 raised to the k. Let's group that with this other 2 times 3 raised to the k. And then notice I've got the -1. And again, a caret symbol to show that I want all this here brought down. Now with these first two terms, I notice that they share a GCF of 3k. So now I'm going to factor out a 3k from just those two terms. I keep my 2 out here. When I factor out 3 to the k, this 3 raised to the k becomes a 1 plus, and this 3 to the k also becomes a 1. So I'm left with 1 times 2, which just gives me 2. And I rewrite my -1. Close that off with a square bracket. And again, I use carets to show that this expression is brought down. Next thing I see is that I can resolve the 2 plus 1 to give me a 3. So let's rewrite doing that. Alright, and now at this point, I notice that I have like bases here, and whenever I'm multiplying factors with like bases, that just means I have to add the exponents. And it's understood that the 3 is understood or implied. It's implied that its exponent is to the first power. So let's rewrite. Here I have 3 to the k plus 1 minus 1. And in this step, I am going to rewrite what I have up here at the top. So this is 2 times 3 raised to the k plus 1 minus 1. And we see that both of these expressions match. So now we've proven by induction that we're able to, that this expression is equal to this series up here for every positive value of n. Alright, that concludes this video by Speller Tutorial Services. Please friend us on Facebook and also subscribe to our YouTube channel, both found under the same name. And as always, thank you again for watching.